Hello! In this video I wanted to revisit something you've already seen a few videos on now, and that is this concept of Bernoulli's equation. And I just wanted to see if we could rewrite this and maybe add in a few extra terms to better describe what happens in fluids. So really quick, let's just recap what Bernoulli's equation actually is. It's a conservation of energy equation. So we're saying that the total energy at some point 1 is equal to the total energy at some point 2 later in the system. And as you might have imagined by the fact that we're talking about total energy, each of these terms has units of energy per volume. And that's fine normally, right? In physics, we often talk about things as having energy, but it turns out that in engineering, energy is not really a useful way of describing fluids. Oftentimes, we don't care about how much energy a fluid has, but how far it's able to travel, especially how high it's able to travel. And so to better describe the behavior of fluids, we have a special unit called hydraulic head. And hydraulic head is a way of converting these velocity and potential and pressure terms all into units of length. And so when we talk about head, we often say that it has, for example, 40 feet of head or 40 meters of head. We always talk about it as having units of length. And what exactly is head? Head is how high a liquid would be able to rise in a standing pipe that's open to the air. And the best way of imagining this is probably just see an example. Let's pretend for a moment that I have a canister of compressed water handy for some reason that's just available to me. I could, and let's say that this canister has a pressure head, HP, a pressure head of 50 feet. If I were to affix a valve and a pipe off to the side of this thing, I would find out that the liquid would be able to rise 50 feet into the air, 50 feet into this vertical pipe before it just comes to a stop. And I could do the same thing with velocity head over here. Let's say that I had some pipe over here and the liquid inside had some velocity head HV 40 feet. I would be able to if I were to put like a little pipe in here that was branching off like this, I would find out that the liquid would be able to rise to some height here of 40 feet. And why is this useful? Well, it tells us immediately how high our liquid would be able to rise, and that tells us whether or not we need to consider adding in pumps or maybe changing the starting elevation of our system in order for the liquid to actually reach its destination. So for example, let's say that I was constructing a building and the building was right on top of an already existing water main. And I know that my building is going to be 100 feet tall. And I just want to find out, well, is the water main going to be able to supply water all the way up to the top of my structure? And so the structure is 100 feet, and I know that my water main, let's say that the city tells me that the water main has a total head, HT total head, of 75 feet. Well, I know immediately that this water is not going to be able to reach the top. It's going to be reached 3/4 of the way. But I know that without having to do any kind of conversions, without having to plug in numbers into any of my equations. Because I was given total head, I already know that it can't reach the top. And so you can see why hydraulic head might be a useful form for this type of thing, especially when we're talking about structure or talking about fluids. It tells us immediately whether or not we need to add pumps into our system. And so how would we rewrite our equation in order to take this into account? Well, we look at this and we say, well, this h term, this already has units of length. So why don't I just rearrange all this, divide everything by rho g in order to get everything with the right units? And that's exactly what I'll do. And if I do that, I find out that my first two terms actually become a little bit simpler, I think. My pressure term becomes a little bit more complicated, but because this is a more useful unit, it actually saves us time in the long run. And I get a form of the Bernoulli's equation that looks like this. And this is called the head form of the Bernoulli's equation. But you remember when I was looking at this example, I already said that I needed to add a pump into my system, right? I needed to add in some kind of pump in order for my liquid to be able to reach the top of my structure. And let's say that I do add in a pump, H pump, is equal to 40 feet, and the liquid is now able to rise well above the top of the building, so the people at the top floor should have plenty of water pressure and water velocity when they turn on their sinks and faucets. But how would I add this into my Bernoulli's equation? Well, I'm adding energy in, so I'll just add this into the right-hand side. I'll just say that I'm just going to add in some H pump term here on the left-hand side. So if I do that, you might say, well, if I'm adding energy, then I must have ways of taking out energy as well, right? And it turns out that there is, although you don't often see this except for a few specialized cases. So the most common example is a hydroelectric dam, where I have water on one side of the dam trying to get through the dam to the other side, and I convert that potential energy, I convert this elevation head and this velocity head into electrical power by running it through a turbine. And so the liquid passes through here, it goes into the turbine, it comes out as electrical energy, and I can take that into account by just adding in this term on the right-hand side here called H turbine. And that's good, but then you'll notice now that my system is 100% efficient. I have no sources of losses in here, right? I have no non-conservative forces. And if you remember back to a lot of examples in physics, almost everything has a non-conservative force acting in it. It has some sort of loss in the system, usually in the form of friction or air resistance. And so I have to take into account losses in my system somehow, but where do those losses come from? And it turns out that I actually have two sources of losses. I have major losses or friction losses, and I have minor losses. These are normally called minor or fitting losses. So what is a major or a friction loss? Well, in my pipe, it turns out that the liquid doesn't travel at a uniform velocity. The liquid travels fastest at the center and it travels slowest at the edges. The pipe actually slows the liquid down as it gets closer and closer to the edge of the pipe, and the liquid travels fastest when it's farthest away from the pipe. So the pipe itself actually contributes quite a bit of losses, and we call it a major loss because it acts along the entire system, right? The liquid is always traveling in a pipe, and so if you have a very long pipe, you have a much larger amount of loss, and also if you have a very small diameter pipe, you can also have a very large amount of loss in your system. And these two terms this concept of friction loss becomes a very big source of energy loss in a system. In fact, you need to add pumps periodically into larger systems to make sure the liquid is able to keep traveling through the pipe. Minor losses are a result of things called fittings. So you could have, for example, if you think about pipes, pipes don't always travel in a straight line. They often have corners, or they have junctions where a liquid suddenly goes from, for example, one branch to two branches. And you also have things like condensers. So you have liquid traveling through a large pipe and it gets condensed down into a smaller diameter pipe. And each of these things is a source of loss, but because these are quantifiable, right? You only have n number of fittings in a system. These are typically called minor losses because they have a much smaller effect overall in your system. And as with H pump and H turbine, we just add this in by adding in this extra term here called H pump. What am I saying? We have this extra loss term which we just add in by saying H loss. And so this is the more complete form of the Bernoulli's equation that we often use for most of our fluid mechanics purposes. So it takes into account most of the sources of gain and loss in our system, and it's written in a form that is more useful to us, right? It's written in terms of hydraulic head, which is a more useful and a more common unit of measurement when we're talking about fluid mechanics.